Tiles Analysis Chapter 3, Part 2. This is going to be about Cartesian products and cardinality. Let's start with Cartesian products, which is 3.5. So a Cartesian product, let's start with the notion of an ordered pair. So an ordered pair can be, we'll just define it with two terms, but essentially it's like a set, right? Where you have two different elements, or like n different elements. But the notion of equality of an ordered pair is that these two are equal if and only if x is equal to x prime, y is equal to y prime. Namely, something like 2, 3 is not equal to 3, 2. So that's where we get the notion of like an ordered pair, right? So, of course, we can extend this ordered pair to like n different components. One way to see this, I guess, is let's say that we have, let's say that we have like x and yz as an ordered pair. And we can consider this like isomorphic to x, y, z. Right? And so that we can extend this to like n different elements by induction. And let's get into Cartesian products. So we denote the Cartesian product x times y. So it's a product of sets. So the product of sets is denoted as, it's a new set, right? A product of set is a set. So it's the set of all ordered pairs x, y, such that x is in x and y is in y. So namely, the cardinality of x cross y is the cardinality of x times the cardinality of y. So let's get an example, right? So if I consider the set 1, 2, 3 times the set ABC, I'll just do AB. I don't want to write down all that thing. I get 1A, I get 2A, I get 3A, I get 1B, I get 2B, I get 3B, and likewise for C. Wait, no, there's no, it's just A and B. Oh, there's no C. Okay, so we can see that the cardinality of this is 3 times 2, which is equal to 6. So one thing that we can do with cardinality is to, or not cardinality, one thing that we can do with this n-tuple is to extend it to like, we can write an n-tuple, right, as xi, where 1 is equal to I less than or equal to n, right? So namely, we can say that this is equal to x1, x2, ... xn. That's just a compact way of writing it. And the definition is the same for like the two n-tuples are equal if and only if every component at the same index is equal. And likewise, for the cardinality product, we can write the product of these n-tuples. So we have x1, x2 to xn are all sets. If we take the product of these sets, we get the set where we're looping over all n-tuples where each xi is in that larger xi. And of course, this is for all 1 less than or equal to I less than or equal to n. That's nice. We can extend this. But one thing about this is it's finite, right? So if it wasn't finite, if this was true for infinite, that would be a nice way to get the axiom of choice for free. But unfortunately, we can't do that. But what we can get for free is finite choice. So remember last video, we did single choice, right? Single choice states that if for any non-empty set, we can choose an element, or there exists an element, right? Finite choice will say, if we have finitely many non-empty sets, we can choose an element from each of the non-empty sets. How do we do this? Well, I should probably, why do we need this n-tuple? Because I'll write it down formally. So we say, let xi be non-empty, and we'll say like 1 less than or equal to I less than or equal to n. So we can say there exists the n-tuple xi 1 less than or equal to I less than or equal to n, where each xi is in xi. So same thing here. Instead of having it just for 1, we have it for 1, 2, all the way up until n. Now, we can say that this finite choice is true. This is actually equivalent to saying that the product 1 less than or equal to I less than or equal to n of the xi's is non-empty. Why? Because the product will give us these i-tuples, right? And we can actually prove that this product is empty if and only if we have an empty set. So how I would prove this is using induction. But I do want to take a look at that real quick, where we have the product of these things. And I want to prove that the product of this is equal to the empty set if and only if xi is equal to the empty set for some xi, for some like I in that range. I'll say xj, where 1 less than or equal to j less than or equal to n. So how do I prove this? Well, let's start with the if, right? This way. So if states that if we have this, right, then we have like one of them has to be this. So how would we prove this? Well, let's do it by contrapositive, right? Let's assume the contrapositive of this is this. And this is finite choice. Finite choice is proved by using the lemma of single choice and induction. So that's the if done. For the only if, we get if xj is equal to the empty set, then the product 1 less than or equal to I less than or equal to n of xi's is equal to the empty set. All right. So in order to do this, we can consider that what would it mean for something to take a product with the empty set? So if I take a product with the empty set, this is equal to set of all a, b, such that a is in A and B is in the empty set. However, this B is never in the empty set, right? So there exists no element such that this hypothesis is true. And if there exists no element such that this set builder is true, it's the empty set. And likewise, if we have n of these, it's the same thing, right? We find that term where it says xi is equal in the empty set. Because this is always false, we can never have a set like that. All right, let's move on to cardinality. So cardinality, we denote cardinality by, so cardinality is really the size of a set, right? But we can't really denote size unless we know what it means to have equal size. So we say that sets X and set Y have equal cardinality. This is the definition. This is a definition of cardinality. This is not something we have to prove. This is a definition. If there exists a bijection from X to Y. So we can pair up the elements, right? That's what a bijection means. We can go forwards and backwards. All right. Now, one thing about equal cardinality is we want to prove it's an equivalence relation, right? So an equivalence relation will satisfy its symmetric, namely x equal to y if and only if y equals to x. This is not hard to prove. It's just bijection has an inverse, right? And the inverse is a bijection. We also have if x is equal to y and y is equal to z, then we have x is equal to z. In order to do this, we can prove, so in order to do this actually, we can prove that if x to y is a bijection and y to z is a bijection, then let's call this map F. Let's call this map G. And the composition map, which takes x to z, is a bijection. So in order to do this, it's not hard to prove. Actually, you just you can consider f of g, and you use the properties that it's injective and surjective, and you can get to it. Or you have to. So for example, I'll just start off the proof and maybe you can finish it from there. I'll say f of g of x is from the map, it's a map from the set x, the map z. So what does f of g of x do? Well, it's f of g of x, right? So let's say I say f of g of a is equal to f of g of b. Well, then this would mean f of g of a is equal to f of g of b. But because f is injective, we can say that g of a equals g of b. And because g is injective, we get a equals b. Surjective, you just do the other part of it. I'll let you do that on your own. All right. Oh, and we also have symmetry, that cardinality of x is equal to the cardinality of x. This is also not hard to prove. You just show that there exists a bijection from x onto itself. Namely, that bijection is the identity map. All right. Now we know finite cardinality. So finite cardinality is where we say a set has two elements. But what we're really doing there is bijecting the set to the real numbers. So let's say I have ABC, right? I'm bijecting this set to 1, 2, 3 to say that it has 3 elements. In general, if I have a set with, we say a set has n elements. So we say the cardinality of x equals n if and only if there exists a bijection x to the set where we have 1 less than or equal to I less than or equal to n. Well, maybe I should probably go. We have the set of all i's in the natural numbers such that 1 is less than or equal to I less than or equal to n. So you have the set 1, it's the interval 1 to n, right? This is how we denote the interval 1 to n. All right then. Now, one thing with cardinality is that it's nice to know that cardinality is unique. Namely, if we have, if x has cardinality m, and x, so let's say we have x to be equal cardinality with y, and x to be equal cardinality with z. So in other words, let's denote the cardinality of y with little y, cardinality of z with little z, then we have y equals z. Now, how do we do this? In order to do this, we need a lemma. So the lemma that we need is that if n is greater than or equal to 1, and x has cardinality n, and if n is equal to 0, you can never have negative cardinality. And if x has cardinality 0, then it's the empty set. Then x is non-empty. This part is easy, right? You just show the only set that is empty is with cardinality 0. And for any x, so we're taking an element of x and we're taking the set difference of x and x. And we're saying that has cardinality of n minus 1. Basically, it's saying if we have a finite set and we remove an element, then that set has cardinality n minus 1. All right, then. So how we can do this? We can denote... so let's just show that there exists a bijection. Let's say x has cardinality n. Let's work with what we have. That means that there's a bijection from x. Proof. Bijection from x to the set 1, we'll go over I and n, such that 1 less than or equal to I less than or equal to n. All right. And now we say there's actually a bijection from x to this to the set n minus 1. Now, how do we show this? Well, we can show that there's a bijection from the set to 1 less than or equal to I less than or equal to n minus 1. How do we work with this? So essentially, we can construct the bijection. I'll just do an outline. I'm not going to go over the full proof, but you can do that on your own. But basically, the outline of this function is that if x is less than y, well, I'll just say for all y in this, right? If I'll say that if if y is less than x, sorry, then we'll let's denote this map with f, this original map with f. Then I'll say that our new map, g of y is equal to g of x. So if we have anything less with it, we just stick with the original. But if y is greater than x, y can't be equal to x because we're removing x. Then we will say that g of y is equal to f of x minus 1. And we see that this is actually a bijection, right? Because we're going over all elements. This contains all y and y. And it bijects to the set I less than or equal to I and n of 1 less than or equal to I less than or equal to n minus 1. So with this lemma, what we can prove is that cardinality is unique, right? And you just do this by induction. You say that, for cardinality is unique. So base case is not hard to prove because the empty set cannot have any elements. But you say, okay, let's say I have x equal to m and y equal to n. Then we consider, by finite choice, we can choose an element and remove that, right? So x, set difference x. This is an element of x. This is big X and small x. That's equal to m minus 1. So we can apply the step beforehand, right? Because this has cardinality of the step beforehand. So we say, now we use the thing beforehand, and we can prove that these two actually have equal cardinality. All right. The next theorem is that n is infinite. This is also not hard to prove. You just show that, if n was finite, then we can, if n was finite, then there's just a bijection from n onto the set 1 less than or equal to I less than or equal to n. And when this happens, you run into problems, I'll say, because when you do that, you can say, okay, well, what if I just have n++? Because every element has a successor. So no matter what we have, there's always going to be something more that we can have. Finally, let's go over cardinality arithmetic. Some of these I'm not going to go over because they're really just like combinatorics. But so one is that if x is finite, we can say that the cardinality of x union an element of x is equal to the cardinality of x plus 1. So the opposite of what we did before. Now we'll say that if x and y is finite, then the cardinality of x union y is less than or equal to x, cardinality of x plus cardinality of y. This is the triangle inequality. We'll say that if x is finite, I'll just assume that x, y are finite for all of these. Y is a subset of x implies that y, the cardinality of y is strictly less, or not strictly less, is less than or equal to the cardinality of x. We'll also show that if I have a function that takes x to y, then the cardinality of f, so the range of the function, is less than or equal to the thing of the function. These are equal if it's injective. And the other two are just combinatorics statements, like the cardinality of y to the x is equal to the cardinality of y to the cardinality of x. Yeah, but that's it for cardinality. We'll see you